Welcome to all of you. So the title of our paper is a noise robust technique for detecting vowels in speech signal. Authors of this paper are Avinash Kumar, Syed Shahnazuddin and myself Waqar Ahmad. So I am an assistant professor at NIT Calicut, Kozhikode, India. So the basic outline of this paper is first I will give some introduction of the paper or introduction of our work. Then I will discuss the variational mode decomposition method that we have employed for detecting the vowels. Then by proposed method of detecting the vowels, where we have used the variational mode decomposition method. Then I will discuss the experimental setup and then resultant discussion, and finally we will conclude with a conclusion. So let us first, this is the introduction. So basically all these vowels are most prominent regions in a speech signal due to their three very important attributes. The first attribute is they have larger amplitude. They are also nearly periodic, and these vowel regions are of longer duration. And the instant of time where a vowel unit start is called vowel onset point, and when the vowel unit ends, that is called vowel end points or VEP. The dominant characteristic of the excitation source as well as the vocal tract filter responses are reflected at these frequencies, that is vowel onset points and vowel end points. Okay, so this accurate detection of vowels and their corresponding vowel onset points and vowel end points have been effectively employed in various speech-based applications. And due to similarity in production characteristic, most of these method fail to detect the vowels and vowel onset points in the case of semi-vowel clusters and diphthongs. So in this work, we have explored the variational mode decomposition method for detection of vowels in a given speech samples in both the clean as well as in the noisy condition. Okay. We have also used the variational mode functions, that is VMFs, to detect those regions in the speech sequence which are of high energy and exhibit periodicity, that is the vowel region. So this VMD algorithm basically breaks the signal into several narrowband variational mode functions or VMFs, and each of the VMFs in turn has a compact frequency support around a center frequency. Okay, and then during the optimization step, the sum of the bandwidth of the modes is minimized subject to the condition that the sum of the mode exactly reconstruct the original signal. So this is the proposed method. And the first, the speech signal is first decomposed in a number of VMS using the VMD as follows. So here we decompose the given speech signal into 8 VMFs. Okay, so the figure of each MF has been shown, where you can easily see that all these VMFs are around some compact frequency. Okay, around some central frequency. So the and VMFs whose center frequency corresponding to 100 and 5,000 hertz frequency bands are selected. Okay, then the non-local means estimation is employed to determine the sum of weight values for each samples in the reconstructed speech signal. Then the significant transition point in the SWV, that is sum of weight values, are then detected by convolving it with the first order difference of Gaussian windows. Okay, then the valleys and peaks corresponding to vowel onset points and vowel end points respectively, and these regions between them are selected as vowels. So in experimental setup, we have used a test set that consists of 400 utterances from equal number of male and female speaker from timid database, and we have also used the noise 692 database for simulating noisy test conditions. Our development set consists of 200 utterance was used for optimizing the tunable parameters. So basically you can see that the first diagram is showing a clean speech segment from the timid database, and reference marking of for the sound units. Okay, and then the B part, we have shown some of the weight values obtained by using non-local mean estimation of the speech signal. And then at the third figure, or C, figures number C, the solid line shows the vowel detection evidence obtained from convolving the SWV with FOG-D windows. Okay, and then the reference vowel regions are depicted by black lines here, where the blue lines represent the detected vowel regions. Okay, the part D, that represents the speech signal reconstructed after selecting only VMF2 to VMF6. So we have discarded the VMF1, and SWV obtained by processing these VMFs reconstructed speech signal has been shown in E. And then the vowel detection evidence, the reference and detected vowel regions has been shown in F. So where the black window is showing the detected vowels regions, okay, and blue lines represent the detected vowel regions. Okay. So in this figure 2, a segment of noisy speech with reference marking has been shown in A, and then the sum of the weight values obtained by using non-local mean estimation of the speech signal has been shown in B, and then the solid lines shows the vowel detection evidence obtained after convolving the SWV with FOG-D windows, and the reference vowel regions are depicted by the black lines, while the blue lines represent the detected vowel regions. Okay, then in D, we have shown the speech signal reconstructed after selecting VMF2 to VMF6, and then the SWV obtained by processing the variation mode functions reconstructed speech signal. Okay, and then the vowel detection evidence and the reference and detected vowel regions has been shown in F. So the proposed method is compared with the three existing method that has been named as CUMBV, EVI, SPEGCI, and NLM-SC respectively. The performance of these existing and the proposed techniques are measured using the following metric. So for vowel, we have used identification rate and spurious rate. What is identification rate is? It is actually the percentage of reference vowel that match with the detected vowels, and the spurious rate is the percentage of detected vowels which lie outside the reference vowel region. And for vowel onset points and vowel end points, we have used again two metric. Again, the first one is identification rate and the second is spurious rate. So for VOP and VEP, the identification rate is the percentage of the reference VOPs and VEPs that match with detected VOPs and VEPs within the predefined deviations, and that is measured in millisecond. And the spurious rate is the percentage of detected VOP and VEPs which are detected outside the reference vowel region. So these are the result. So the result is obtained both the clean as well as the noisy conditions. So what we can easily observe that our proposed method outperform for both clean as well as the uh, noisy condition case. Okay. So also the performance of the proposed and explored technique for task of VOP and VEP, that is vowel onset points and vowel end points, has been shown in this table. So again, in this case also, you can see that for both VOP detection and VEP detection, the proposed method outperformed the existing method for all the cases, that is both in clean as well as in the noisy condition. So the basic, this VMD algorithm, that is variational mode decomposition algorithm, has been explored for suppressing the high frequency content and in order to effectively detect the vowel in a speech signal. So this proposed technique outperforms the existing one. The proposed features is discriminative and robust toward the environmental degradation, as we have already seen that this method outperforms both in the clean case and also the noisy case. Okay, Thank you.